Welcome. Take a slow, gentle breath in, and as you exhale, imagine holding a small crystal in your hand. Its surface feels cool and smooth, its edges precise, its shape calm and steady. Crystals have fascinated people for thousands of years because of their remarkable order. They are one of nature's clearest examples of structure, symmetry, and quiet persistence. A crystal is a solid material whose atoms are arranged in a highly ordered, repeating pattern. This pattern extends in all directions, forming what scientists call a crystal lattice. Unlike glass or many plastics, where atoms are arranged randomly, crystals grow with internal order that repeats again and again. This repeating structure gives crystals their flat faces, sharp edges, and consistent angles. At the smallest scale, crystals begin with atoms and molecules. These tiny building blocks bond together in specific ways depending on their chemical properties. When conditions are stable, the particles settle into repeating geometric arrangements. Over time, layer upon layer builds outward, maintaining the same pattern. This steady growth can produce shapes that appear almost mathematical in their precision. Crystals form in many environments across the Earth. Some grow deep underground from molten rock. Others form when mineral-rich water slowly evaporates. Still others develop when heat and pressure reshape existing rocks. Despite these different origins, the underlying principle remains the same. Particles arrange themselves into stable, repeating structures. The word crystal comes from the Greek word kristallos, meaning ice. Ancient observers believed clear quartz was permanently frozen water because of its glass-like appearance. Today, we understand that quartz is silicon dioxide, one of the most abundant minerals in Earth's crust. Its clarity and hardness made it a source of fascination long before its true composition was known. Crystals can be made of a single element, such as diamond, which consists entirely of carbon atoms. They can also be compounds, like halite, known commonly as rock salt, which forms from sodium and chlorine. In both cases, the atoms bond in precise arrangements that repeat in three-dimensional space. One of the defining features of crystals is their symmetry. If you rotate many crystals by certain angles, they appear unchanged. This symmetry reflects the internal lattice structure. For example, cubic crystals such as halite form perfect cubes because their atomic arrangement repeats equally in three directions. Another important characteristic is cleavage, which describes how a crystal breaks along flat planes. Because of their orderly structure, many crystals split along predictable lines. Mica, for instance, separates into thin, flexible sheets due to weak bonds between its layers. This property made mica useful historically as a heat-resistant window material. Hardness is also a key feature. The Mohs scale ranks minerals from 1 to 10 based on their resistance to scratching. Talc sits at the softest end, while diamond, the hardest natural substance, ranks at 10. This hardness arises from the strength of bonds within the crystal lattice. Crystals do not always grow into large, visible forms. Many exist as microscopic grains within rocks. Granite, for example, contains visible crystals of quartz, feldspar, and mica interlocked together. Basalt, by contrast, cools so quickly that its crystals remain extremely small. Time plays an important role in crystal formation. Slow cooling or gradual evaporation allows atoms to arrange themselves into well-ordered structures. Rapid changes often produce smaller crystals, or even glass, where atoms do not have time to settle into a lattice. Temperature, pressure, and chemical composition all influence how crystals form. A slight change in conditions can alter crystal size, shape, or even which mineral forms. This sensitivity makes crystals valuable records of the environments in which they grew. Crystals are not limited to rocks and minerals. Snowflakes are also crystals, formed from water vapor freezing in the atmosphere. Each snowflake develops a unique pattern influenced by temperature and humidity as it falls through the air. Despite their delicate forms, they obey the same principles of repeating molecular structure. Salt crystals can form when seawater evaporates. As water molecules leave, sodium and chloride ions bond into cubic structures. These tiny cubes accumulate to form salt flats and deposits that can stretch across vast landscapes. In caves, mineral-rich water drips slowly from ceilings, depositing calcite. Over many years, this process forms stalactites and stalagmites, each composed of countless tiny crystals growing together. Their slow formation is a reminder of nature's patience. Some crystals grow to enormous sizes. In certain underground chambers, gypsum crystals have reached lengths of over 10 meters. These giants formed under stable conditions that allowed uninterrupted growth for thousands of years. The colors of crystals often come from trace elements. Pure quartz is clear, but small amounts of iron can create amethyst's purple hue. Chromium can give corundum a red color, forming ruby, while other trace elements produce sapphires, blues, and yellows. Light interacts with crystals in unique ways. Some crystals refract light, bending it as it passes through. Others display double refraction, splitting light into two rays. Calcite is well known for this property, producing a doubled image when viewed through a clear sample. Certain crystals exhibit piezoelectricity, generating an electrical charge when pressure is applied. Quartz crystals are used in watches and electronic devices for this reason. Their consistent vibration under electrical current helps keep precise time. Crystals also play a role in geology by helping scientists understand Earth's history. The size and arrangement of crystals in igneous rocks reveal cooling rates. Metamorphic crystals indicate pressure and temperature conditions. These natural records allow geologists to reconstruct past environments. Although crystals can appear still and unchanging, their formation is a dynamic process. Atoms move, bond, and settle into place, guided by physical laws. Over time, these tiny interactions create structures of remarkable clarity and order. As you imagine a crystal forming slowly in darkness beneath the Earth's surface, consider the quiet patience required for its growth. Layer by layer, particle by particle, it develops its shape without haste. There is no urgency in this process, only steady progression toward balance. Crystals remind us that order can emerge from simple rules repeated over time. Their calm geometry reflects stability, while their variety shows how subtle changes in conditions create endless forms. From microscopic grains to towering formations, crystals are nature's expression of structure and stillness. Let your thoughts settle like particles in a cooling solution. gently arranging themselves into calm patterns. Picture a crystal growing slowly, silently, in perfect symmetry. With each breath, allow the steady rhythm of its formation to guide you toward rest. Take a slow, steady breath in and imagine drifting downward into a world far smaller than grains of sand. In this quiet realm, crystals begin with atoms, tiny particles moving gently, guided by forces that encourage balance and stability. In this microscopic stillness, structure emerges from repetition, and repetition becomes form. Atoms are composed of a central nucleus surrounded by electrons. The nucleus contains protons and neutrons, while electrons occupy regions known as orbitals. The number of protons in the nucleus determines the element, whether it is silicon, carbon, oxygen, sodium, or iron. Each element forms bonds in predictable ways, and these bonding patterns determine how crystals grow. When atoms bond, they seek stable arrangements. Some share electrons in covalent bonds, creating strong connections as seen in diamond and quartz. Others transfer electrons, forming ionic bonds, such as those in halite. These bonds act like invisible links, holding atoms in precise positions relative to one another. As atoms bond repeatedly, they form a crystal lattice. A lattice is a three-dimensional framework that repeats in space. Imagine a pattern extending outward in every direction, identical in structure, no matter how far it grows. This repeating arrangement is what gives crystals their characteristic shapes and symmetry. The smallest repeating unit of a crystal lattice is called the unit cell. This tiny structure contains the essential arrangement of atoms that defines the entire crystal. By repeating the unit cell again and again, the crystal builds its full form. Even the largest crystal can be traced back to this simple, repeating foundation. There are several basic types of crystal systems, each defined by the shape of its unit cell. These include cubic, tetragonal, orthorhombic, hexagonal, trigonal, monoclinic, and triclinic systems. Each system reflects a different arrangement of axes and angles, creating distinct external shapes. In the cubic system, all sides of the unit cell are equal, and all angles are 90 degrees. This symmetry produces cubes and related shapes. Minerals such as halite and pyrite often form cubic crystals, their faces smooth and their edges sharp, reflecting the internal order of their lattices. The hexagonal system features six-fold symmetry. Quartz is a well-known example, often forming six-sided prisms with pointed ends. This shape arises from the hexagonal arrangement of silicon and oxygen atoms within its structure. In the tetragonal system, two axes are equal, while the third differs in length. This arrangement produces elongated forms, such as the crystals of zircon. Each crystal system represents a different way atoms can organize themselves while maintaining stability. Temperature plays a significant role in lattice formation. At higher temperatures, atoms vibrate more vigorously, making it harder for them to settle into stable positions. As temperature decreases, atomic motion slows, allowing bonds to form and lattices to develop. This gradual calming of motion is essential for crystal growth. Pressure also influences atomic arrangement. Deep within the Earth, immense pressure forces atoms closer together, sometimes creating denser crystal structures. Graphite and diamond both composed of carbon, form under different pressure conditions, resulting in dramatically different structures and properties. Impurities can enter a crystal lattice during growth. These foreign atoms may replace or sit between the regular atoms. Even small amounts of impurities can change a crystal's color, electrical properties, or strength. This subtle variation adds diversity to crystal forms found in nature. Crystal lattices are not always perfect. Defects can occur when atoms are missing, displaced, or substituted. These imperfections are known as vacancies, interstitial defects, or substitutional defects. While the word defect may sound negative, these irregularities often influence a crystal's physical properties in useful ways. For example, certain defects in gemstones create color centers, which absorb specific wavelengths of light. In diamonds, defects involving nitrogen can produce yellow hues. These tiny variations at the atomic level shape the beauty we see with the naked eye. Another fascinating aspect of crystal lattices is anisotropy. This means that a crystal's properties can vary depending on direction. Light, heat, and electricity may travel differently along different axes of a crystal. This directional behavior arises directly from the ordered arrangement of atoms. In contrast, materials like glass are isotropic, meaning their properties are the same in all directions. This difference highlights the unique nature of crystalline order compared to amorphous solids, where atoms lack a repeating pattern. Crystal growth begins with nucleation, the formation of a tiny stable cluster of atoms. Once a nucleus forms, additional atoms attach themselves in alignment with the existing lattice. This process continues layer by layer, building the crystal outward. The calmer and more stable the environment, the more orderly the growth. Supersaturated solutions often encourage nucleation. When a liquid contains more dissolved material than it can normally hold, even a small disturbance can trigger crystal formation. Sugar crystals forming on a string in cooled syrup demonstrate this principle in a gentle, observable way. In nature, similar processes occur when mineral-rich water cools or evaporates. Dissolved ions settle into lattices, forming crystals that may line rock cavities or fill fractures. Over time, these crystals can grow into sparkling formations hidden within the earth. The geometry of a crystal lattice determines how a crystal interacts with light. Transparent crystals allow light to pass through with minimal scattering, while others reflect or refract light due to their internal structure. The angles between crystal faces correspond directly to the angles within the lattice. This consistency is known as the law of constancy of interfacial angles. No matter the size of a crystal, the angles between corresponding faces remain the same for a given mineral. This principle helped early scientists recognize that crystals grow according to internal order rather than random chance. Some crystals form twins, where two lattices grow together in symmetrical patterns. Twinning can create mirror-like arrangements or repeated segments within a single crystal. These patterns add visual complexity while still reflecting underlying order. As crystals grow, they compete for space and resources. In crowded environments, crystals may grow irregularly, interlocking with neighbors. In open cavities, they can develop well-formed faces. This difference explains why some crystals appear as perfect geometric shapes, while others are embedded in rock. Time remains one of the most important factors in crystal lattice development. Slow, uninterrupted growth allows atoms to align properly, producing clarity and symmetry. Rapid growth often leads to smaller, less ordered crystals. Patience, even at the atomic level, shapes the final form. Imagine this slow assembly continuing silently in darkness. Atoms settling into place, vibrations easing, bonds forming in quiet succession. There is no sound, no rush, only the steady rhythm of structure emerging from motion. As you rest, picture a lattice extending outward in perfect repetition, each unit cell aligning with the next. The pattern continues without strain, balanced and calm. In this gentle order, there is a sense of stability that invites your thoughts to slow and settle. Allow your breathing to match this steady rhythm. Inhale as atoms come together. Exhale as the lattice extends. With each cycle, the structure grows more complete, more balanced, more at rest. Take a slow, steady breath in and imagine descending deep beneath the Earth's surface, far below soil and stone, into regions where heat is constant and immense. Here, rock exists not as solid ground, but as molten material known as magma. Within this glowing, fluid environment, many crystals begin their long and patient formation. Magma forms when rock melts under high temperatures and pressure conditions within the Earth. This molten mixture contains a variety of chemical elements, including silicon, oxygen, aluminum, iron, magnesium, calcium, sodium, and potassium. As magma slowly cools, these elements begin to bond together, forming minerals that crystallize from the melt. Crystallization from magma is a gradual process. At very high temperatures, atoms move freely within the molten rock. As cooling begins, atomic motion slows, allowing bonds to form. The first minerals to crystallize are those stable at the highest temperatures. These early forming minerals often include olivine and pyroxene, which contain iron and magnesium. As the temperature continues to drop, other minerals begin to form. Feldspar minerals, rich in aluminum and silica, crystallize next. Quartz, composed of silicon and oxygen, typically forms at lower temperatures near the final stages of cooling. This sequence reflects a principle known as fractional crystallization, where minerals form in a predictable order based on their stability. When crystals form in magma, they may remain suspended in the molten material or settle due to gravity. Denser minerals often sink toward the bottom of a magma chamber, while lighter ones remain suspended. This separation can influence the composition of the remaining melt, leading to the formation of different rock types. If magma cools slowly beneath the Earth's surface, it forms intrusive, igneous rocks, also called plutonic rocks. Granite is a common example. Because cooling occurs over thousands to millions of years, crystals have time to grow large and well-defined. The visible grains of quartz, feldspar, and mica in granite reflect this slow crystallization process. In contrast, magma that reaches the surface becomes lava and cools rapidly. This rapid cooling produces extrusive igneous rocks, such as basalt and obsidian. In basalt, crystals are too small to see without magnification because atoms had little time to arrange into large lattices. Obsidian forms so quickly that a crystal structure does not develop, resulting in volcanic glass. The rate of cooling plays a crucial role in crystal size. Slow cooling allows atoms to migrate to growing crystal surfaces, producing larger crystals. Rapid cooling traps atoms in place, creating fine-grained or glassy textures. This relationship between cooling rate and crystal size helps geologists interpret the history of volcanic regions. Sometimes magma cools in two stages, producing porphyritic textures. In this case, large crystals called phenocrysts form during slow cooling underground. Later, the remaining melt erupts and cools quickly, forming a fine-grained matrix around the larger crystals. This texture records a complex cooling history within a single rock. Volatile substances within magma, such as water vapor, carbon dioxide, and sulfur gases, also influence crystal formation. These gases remain dissolved under high pressure, deep underground. As magma rises and pressure decreases, gases escape, creating bubbles. The presence of volatiles lowers the melting point of minerals and can accelerate crystal growth. Water, in particular, plays an important role. It reduces viscosity, allowing ions to move more freely within the melt. This increased mobility can promote the growth of larger, well-formed crystals. In some environments, water-rich magma produces pegmatites, which contain exceptionally large crystals of quartz, feldspar, and mica. Pegmatites are remarkable for their crystal size. Some quartz crystals found in pegmatites can exceed several meters in length. These giant crystals formed in magma pockets, rich in water and rare elements, where slow cooling allowed uninterrupted growth. Chemical composition also determines which crystals form. Magma rich in silica tends to produce light-colored minerals like quartz and feldspar. Magma lower in silica forms darker minerals such as olivine and pyroxene. This variation gives rise to a wide range of igneous rocks, each with distinct crystal assemblages. Crystals forming in magma often display well-defined faces if they grow in open spaces. However, in crowded conditions, crystals may grow against one another, producing irregular shapes. This interlocking texture strengthens the resulting rock, making igneous formations some of the most durable structures in the Earth's crust. Zoning can occur within individual crystals as magma composition changes during cooling. A crystal may develop layers with slightly different chemical compositions, visible as subtle color bands. These zones provide clues about changing conditions during crystal growth. Some crystals incorporate trace elements present in the magma. For example, small amounts of chromium can color certain minerals green, while iron can produce reds, browns, or yellows. These variations arise from tiny substitutions within the crystal lattice. As magma cools further, the remaining melt becomes enriched in elements that do not fit easily into earlier forming minerals. This residual melt can produce rare minerals containing lithium, beryllium, and other uncommon elements. Such minerals often form in late-stage pegmatites and hydrothermal veins. hydrothermal fluids derived from cooling magma can circulate through surrounding rocks. These hot, mineral-rich fluids deposit crystals in fractures and cavities. Quartz veins, for instance, form when silica-rich fluids cool and precipitate crystalline quartz within rock cracks. Over time, magma chambers solidify completely, preserving a record of crystallization within their rocks. By studying crystal size, composition, and arrangement, geologists can infer cooling rates, magma composition, and the presence of volatiles during formation. Imagine this slow cooling deep underground, a vast chamber of molten rock gradually losing heat. Atoms drift, bonds form, and tiny crystal nuclei appear. Over centuries, these nuclei grow, their lattices extending in quiet symmetry. There is no sudden change, only a steady progression towards solidity. As you picture this process, allow your thoughts to cool and settle, just as magma does. The heat of the day fades, replaced by calm stillness. Each breath slows, mirroring the gradual crystallization occurring far below the surface. In this deep, silent environment, crystals form without urgency. Their growth is patient, guided by physical laws and gentle changes in temperature and pressure. The resulting structures, hidden within rock, remain as lasting records of this quiet transformation. Let your mind rest on the image of crystals forming in darkness, their shapes emerging slowly from molten beginnings. With each exhale, imagine the magma cooling further, the crystals growing more complete, the environment becoming still and calm. Take a slow, gentle breath in, and imagine standing beside a quiet shoreline at low tide. The air is still, and shallow pools of seawater rest in small hollows in the sand. As warmth from the sun touches the surface, the water slowly disappears into the air. What remains behind is not emptiness, but structure. Tiny crystals forming silently where liquid once flowed. Water is one of the most important agents of crystal formation on Earth. It dissolves minerals from rocks and soil, carrying ions in solution across great distances. When conditions change, when water cools, evaporates, or reacts chemically, these dissolved particles come together, arranging themselves into ordered crystal lattices. Evaporation is one of the simplest ways crystals form from water. As liquid water turns into vapor, the concentration of dissolved minerals increases. Eventually, the solution becomes supersaturated, meaning it contains more dissolved material than it can hold under those conditions. At this point, ions begin to bond, forming tiny crystal nuclei. Once nucleation begins, crystals grow as additional ions attach to the existing lattice. This growth continues as long as the solution remains supersaturated. The process is gradual and steady, often producing well-formed crystals with smooth faces and sharp edges. Salt flats provide a striking example of evaporation-driven crystal growth. In arid regions, shallow lakes or seas evaporate over time, leaving behind thick layers of salt. These deposits often consist of halite crystals, which form perfect cubes due to their cubic lattice structure. Some salt flats stretch for kilometers, reflecting sunlight in soft, shimmering patterns. In coastal environments, sea spray can leave behind delicate salt crystals on rocks and plants. As droplets evaporate, tiny cubes of halite remain, sparkling faintly in the light. Though small, these crystals form through the same orderly processes as larger mineral deposits. Another common evaporate mineral is gypsum, a calcium sulfate compound. Gypsum forms in evaporating lakes and lagoons, often producing layered deposits. In some locations, gypsum crystals grow to impressive sizes, especially where conditions remain stable over long periods. In underground caves, evaporation plays a role in forming delicate crystal structures. When mineral-rich water seeps through rock and enters an open cavern, evaporation can leave behind thin crusts of calcite or gypsum. These deposits may form sparkling coatings on cave walls, sometimes called cave frost. Beyond evaporation, cooling water can also trigger crystal formation. Hot springs, for example, carry dissolved silica and other minerals from deep underground. As the water reaches the surface and cools, silica precipitates to form deposits known as sinter. Over time, these deposits harden into crystalline structures. In geothermal areas, terraces of mineral deposits form as hot water flows and cools. Each step in a terrace marks a location where minerals crystallized from solution. The resulting formations create layered landscapes that reflect the slow, continuous deposition of crystals. Stalactites and stalagmites in caves form through a related process. Rainwater absorbs carbon dioxide from the air and soil, forming a weak carbonic acid. This slightly acidic water dissolves calcium carbonate from limestone rock. When the water drips into a cave, carbon dioxide escapes, and calcite crystals precipitate. Over many years, these calcite crystals accumulate to form stalactites hanging from cave ceilings and stalagmites rising from cave floors. Each droplet leaves behind a microscopic layer of crystals. The growth is slow, often less than a centimeter per century, yet the resulting formations can become massive over time. In desert environments, evaporation can produce crystals beneath the soil surface. As groundwater rises through capillary action and evaporates, minerals crystallize within the soil, forming hard layers known as caliche. These deposits can cement soil particles together, altering the landscape. Evaporate minerals also include sylvite, a potassium chloride mineral, and anhydrite, a calcium sulfate mineral that forms in extremely dry conditions. These minerals record ancient environments where seas once evaporated, leaving behind thick crystalline deposits. Crystal growth from water is influenced by temperature, concentration, and the presence of impurities. Slow evaporation tends to produce larger crystals, while rapid evaporation results in smaller, less defined forms. Impurities can alter crystal shape, creating variations even within the same mineral. The geometry of crystals formed from evaporation reflects their internal lattice structure. Halite forms cubes, gypsum forms tabular crystals, and calcite often develops rhombohedral shapes. These consistent forms arise from the orderly arrangement of atoms during growth. In some cases, crystals form crusts on the surface of evaporating pools, creating fragile patterns that crack and curl as they dry. These patterns, though temporary, demonstrate the dynamic interplay between water, minerals, and air. Seasonal cycles can repeat the process of dissolution and crystallization. During wet periods, minerals dissolve into water. During dry periods, they crystallize again. Over many cycles, this process builds substantial mineral deposits, layer by layer. Even simple household examples reflect these natural processes. When a solution of sugar in water cools and evaporates, sugar crystals form along container walls or strings. Though simple, this process mirrors the formation of natural crystals in evaporating lakes and caves. The clarity of crystals formed from water often depends on the purity of the solution. Clear quartz crystals, for instance, can form from silica-rich fluids under stable conditions. If impurities are present, they may create inclusions, tiny trapped particles or bubbles within the crystal. These inclusions provide valuable information about the environment in which the crystal formed. Trapped fluid bubbles can reveal temperature and pressure conditions, offering a microscopic record of geological history. Imagine a shallow pool slowly drying beneath a warm sky. As the water retreats, tiny crystals appear, first as faint outlines, then as defined shapes. They grow quietly, guided by the steady removal of water and the increasing concentration of minerals. This process is unhurried, unfolding over hours, days, or years. There is no sound, only the silent assembly of atoms into ordered forms. The surface transforms gradually, reflecting light in new patterns as crystals spread. As you rest, picture this gentle transformation: water fading into air, minerals settling into place, structure emerging from stillness. With each breath, allow your thoughts to evaporate like the water, leaving behind calm, orderly patterns. Crystals formed from evaporation remind us that even as something disappears, something else takes shape. In the quiet balance between loss and formation, nature creates forms of lasting beauty and stability. Let your breathing slow, matching the steady rhythm of evaporation and crystallization. Inhale and imagine water rising into the air. Exhale and see crystals forming in its place. With each cycle, the scene becomes more peaceful, more still, and more complete. Take a slow, steady breath in and imagine layers of rock resting deep within the earth, far below mountains and valleys. Over long periods of time, these rocks experience intense heat and pressure. They do not melt into magma, but they change. Within this stillness, crystals begin to grow in new forms, reshaping the rock from the inside. This process is known as metamorphism. It occurs when existing rocks are subjected to temperatures and pressures high enough to alter their mineral structure, yet not high enough to cause complete melting. During metamorphism, atoms rearrange themselves into more stable crystal structures, suited to the new conditions. Metamorphic crystal growth begins at the microscopic level. Minerals within the original rock become unstable under new temperature and pressure conditions. Bonds break and reform, allowing atoms to migrate and assemble into new lattices. Over time, these new crystals grow, often larger and more organized than the minerals they replace. Heat plays a central role in metamorphism. As temperature rises, atomic vibrations increase, enabling atoms to move and reconfigure. This mobility allows minerals to recrystallize into forms that are stable under the prevailing conditions. The process is gradual, occurring over thousands to millions of years. Pressure also shapes crystal growth. Deep within the earth, rocks experience immense pressure from overlying layers. This pressure can compress minerals, forcing atoms into denser arrangements. In some cases, pressure is directional, meaning it acts more strongly in one direction. This directional pressure influences the orientation of growing crystals. When pressure is uniform, crystals tend to grow without a preferred direction. However, under directed pressure, platy or elongated minerals align perpendicular to the force. This alignment creates foliation, a layered texture seen in metamorphic rocks such as slate and schist. Slate forms when shale is subjected to low-grade metamorphism. Clay minerals recrystallize into tiny mica crystals that align in parallel layers. This alignment allows slate to split into thin sheets, a property that has made it useful for roofing and writing surfaces throughout history. As metamorphism progresses to higher grades, larger crystals develop. Schist contains visible mica crystals that shimmer softly in reflected light. These crystals, formed as heat and pressure, allowed atoms to migrate and assemble into larger, well-defined structures. At even higher grades of metamorphism, gneiss forms. In gneiss, minerals separate into light and dark bands, reflecting differences in composition. Quartz and feldspar form lighter layers, while biotite and amphiboly create darker bands. This banding results from mineral segregation during recrystallization. One of the most striking examples of metamorphic crystal growth is garnet. Garnets often form as rounded crystals within metamorphic rocks. They grow as atoms migrate toward a nucleation site, building concentric layers. Some garnets contain inclusions that record earlier stages of growth, preserving a timeline within the crystal. Metamorphic environments can also produce minerals such as kyanite, staurolite, and andalusite, which form under specific pressure and temperature conditions. These minerals serve as indicators, helping geologists determine the conditions under which the rock formed. Recrystallization during metamorphism often increases crystal size. Small, poorly formed grains transform into larger, interlocking crystals. This process strengthens the rock by reducing pore spaces and creating a more cohesive structure. Fluids play an important role in metamorphic crystal growth. Water and other fluids present in rock pores can dissolve ions and transport them to growing crystals. This process, known as metasomatism, allows chemical components to move and contribute to new mineral formation. Hydrothermal fluids associated with metamorphism can deposit crystals in fractures and cavities. Quartz veins commonly form when silica-rich fluids move through cracks and precipitate quartz as conditions change. These veins may contain well-formed crystals lining open spaces. Metamorphic crystal growth often occurs without visible melting. Instead, atoms rearrange in the solid state, guided by pressure, temperature, and chemical environment. This solid-state transformation preserves the rock's overall form while altering its internal structure. The timescale of metamorphism is vast. Crystals grow slowly, sometimes only fractions of a millimeter over centuries. Yet over millions of years, this gradual growth produces rocks with large visible crystals and complex textures. Metamorphic rocks provide valuable records of geological processes. The types of crystals present, their sizes and their orientations reveal the pressures and temperatures experienced during formation. By studying these features, geologists reconstruct the history of mountain building and deep crustal processes. Imagine layers of rock resting quietly under immense weight. Within them, atoms shift, bonds reform, and new crystals emerge. There is no sudden motion, only a slow transformation guided by heat and pressure. As you picture this deep, silent change, allow your thoughts to settle. The weight above becomes a gentle stillness rather than a burden. Each breath mirrors the steady pace of recrystallization, calm and unhurried. In this environment, crystals grow in harmony with their surroundings. They align with pressure, respond to heat, and incorporate available elements. The resulting structures reflect balance and adaptation, formed without haste. Some metamorphic crystals display zoning, where variations in composition create subtle rings. These rings mark changes in conditions during growth, like quiet echoes of the environment's shifting state. Other crystals grow in pressure shadows, protected areas adjacent to larger grains. In these sheltered spaces, minerals can accumulate and crystallize, creating delicate patterns within the rock. Metamorphic processes can also produce marble, formed when limestone recrystallizes under heat and pressure. Calcite crystals grow larger and interlock, creating a dense, uniform rock, prized for sculpture and architecture. Quartzite forms when sandstone undergoes metamorphism. Quartz grains recrystallize and fuse, producing an extremely hard rock. The new crystal bonds eliminate pore spaces, making quartzite resistant to weathering. These transformations illustrate how existing materials can reorganize into more stable forms. Without melting, without dramatic change, atoms shift into new arrangements, creating crystals suited to their environment. As you rest, imagine this quiet reorganization, tiny movements accumulating over immense time, forming structures of strength and beauty. The deep earth remains silent, yet within it, crystals grow steadily. Let your breathing slow further, matching the calm pace of metamorphic change. Inhale, and imagine atoms aligning. Exhale and see crystals expanding within the rock. With each breath, the transformation continues, gentle and complete. Take a slow, calm breath in, and imagine holding a crystal up to soft light. Its faces reflect gentle patterns. Its edges meet at precise angles, and its shape feels balanced and complete. Crystal shapes are not random. They are the visible expression of the orderly arrangement of atoms within. The external form of a crystal is known as its crystal habit. This habit reflects both the internal lattice structure and the conditions under which the crystal grew. Some crystals form long prisms, others develop as cubes, plates, needles, or branching patterns. Despite their variety, these shapes arise from consistent geometric rules. At the heart of crystal shape is symmetry. Symmetry describes how a shape can be rotated, reflected, or repeated while remaining unchanged. Crystals display symmetry because their atomic arrangements repeat in predictable ways. This repetition produces faces and angles that remain constant for each mineral. One of the most noticeable forms of symmetry is rotational symmetry. A crystal has rotational symmetry if it looks the same after being rotated by a certain angle. For example, a cubic crystal can be rotated 90 degrees and still appear unchanged. This symmetry mirrors the cubic arrangement of atoms within its lattice. Reflection symmetry occurs when one half of a crystal mirrors the other. If a plane divides the crystal into two identical halves, the crystal possesses mirror symmetry. Many crystals exhibit multiple planes of symmetry, contributing to their balanced appearance. The angles between crystal faces remain consistent for a given mineral. This principle, known as the law of constancy of interfacial angles, states that no matter how large or small a crystal grows, the angles between corresponding faces remain the same. This consistency helped early scientists understand that crystals grow according to internal order rather than chance. Crystals are classified into 7 crystal systems based on their symmetry and unit cell geometry. These systems include cubic, tetragonal, orthorhombic, hexagonal, trigonal, monoclinic, and triclinic. Each system defines a unique set of axes and angles that determine crystal shape. In the cubic system, crystals form shapes such as cubes, octahedra, and dodecahedra. Minerals like halite, pyrite, and fluorite commonly display cubic symmetry. Their faces meet at right angles, reflecting equal atomic spacing along 3 axes. The hexagonal system produces 6-sided prisms and pyramids. Quartz is a familiar example, often forming elongated hexagonal crystals with pointed ends. Snowflakes, though delicate and temporary, also exhibit hexagonal symmetry due to the structure of ice crystals. The tetragonal system resembles the cubic system, but with one axis longer than the others. This arrangement produces elongated shapes, such as those seen in zircon crystals. Their symmetry remains orderly, though slightly stretched along one direction. Orthorhombic crystals have 3 unequal axes intersecting at right angles. This system produces rectangular prism shapes, as seen in minerals like sulfur and olivine. The angles remain 90 degrees, but the differing axis lengths create distinct proportions. Monoclinic crystals have 3 unequal axes, with one axis tilted. This tilt produces asymmetrical shapes, though internal order remains consistent. Gypsum and orthoclase feldspar often crystallize in the monoclinic system. Triclinic crystals exhibit the least symmetry. All axes are unequal, and none intersect at right angles. Despite this apparent irregularity, triclinic crystals still possess internal order. Minerals such as turquoise and plagioclase feldspar belong to this system. Crystal habit can be influenced by growth conditions. When crystals grow in open spaces, they develop well-formed faces reflecting their symmetry. In crowded environments, they may grow irregularly, their shapes constrained by neighboring crystals. Needle-like crystals, known as acicular habits, form when growth is faster in one direction. Fibrous crystals develop when many thin crystals grow parallel to one another. Tabular crystals form flat plates, reflecting rapid growth along 2 axes and slower growth along the 3rd. Dendritic crystals form branching patterns resembling frost on glass or delicate trees. These patterns occur when growth is rapid and uneven, often in environments with fluctuating conditions. Though intricate in appearance, dendritic patterns still reflect underlying order. Twinning is another phenomenon that influences crystal shape. Crystal twins occur when two or more crystals grow together in symmetrical arrangements. The resulting forms may appear mirrored or repeated, creating complex but orderly patterns. One common twin form is the contact twin, where two crystals share a common plane. Penetration twins occur when crystals grow through one another, forming interlocking shapes. These structures demonstrate how crystals can maintain symmetry even while growing together. Surface features on crystal faces also reflect growth patterns. Striations or fine parallel lines may appear due to variations in growth rate. These markings provide clues about the conditions under which the crystal formed. Crystal symmetry influences how minerals break. Cleavage occurs along planes of weakness within the crystal lattice. Because these planes reflect internal structure, cleavage surfaces often align with crystal faces. Halite breaks into cubes, while calcite breaks into rhombohedra. Fracture, in contrast, occurs when a mineral breaks irregularly. Quartz, for example, exhibits conchoidal fracture, producing smooth, curved surfaces. This fracture pattern arises from the absence of cleavage planes in its lattice. Symmetry also affects how crystals interact with light. Transparent crystals may refract light in predictable ways based on their internal structure. Some crystals display birefringence, splitting light into two rays traveling at different speeds. Calcite is well known for strong birefringence. When placed over text, a clear calcite crystal produces a doubled image. This optical effect arises from the crystal's internal symmetry and directional properties. Color zoning within crystals can follow symmetrical patterns. Variations in trace elements during growth may produce bands or sectors aligned with crystal faces. These patterns reflect changes in environmental conditions during formation. Crystal shapes often inspire architecture and design due to their natural balance. The geometric precision of crystals reflects fundamental physical laws, creating forms that appear both structured and serene. Imagine a crystal growing slowly in a quiet space, each face forming at a precise angle, each edge meeting another in perfect alignment. There is no haste, only the steady repetition of atomic patterns shaping the visible form. As you picture this symmetry, allow your thoughts to settle into gentle order. The balanced geometry of crystals invites a sense of calm, a reminder that structure can arise naturally from simple, repeated patterns. Let your breathing mirror this symmetry. Inhale evenly, exhale evenly, creating a rhythm that feels balanced and steady. With each breath, imagine the crystal becoming more complete, its shape emerging in quiet harmony. In this calm stillness, crystal symmetry becomes a reflection of inner balance, steady, ordered, and at rest. Take a slow breath in and imagine drifting peacefully across the globe, visiting calm and remote places where crystals have grown over thousands or even millions of years. These locations are not hurried or loud. They are steady environments where minerals have formed in stillness, creating structures of remarkable size and clarity. One of the most extraordinary crystal locations lies beneath the desert of northern Mexico, in the Naka mine. Deep underground, a chamber known as the Cave of the Crystals contains enormous gypsum crystals. Some of these crystals reach lengths of more than 10 meters and weigh many tons. They formed in warm, mineral-rich water that remained stable for thousands of years, allowing uninterrupted growth. The gypsum crystals in Naka grew under precise conditions. The cave remained filled with water, saturated with calcium sulfate. At temperatures close to 58 degrees Celsius, the mineral anhydrite became unstable and slowly converted into gypsum. As this transformation released calcium and sulfate ions, they crystallized into giant transparent beams. Traveling in your imagination to Brazil, you may picture the vast deposits of quartz crystals found in the state of Minas Gerais. This region is known for producing large, clear quartz crystals, as well as amethyst geodes lined with purple crystals. These formations developed in volcanic rock cavities, where silica-rich fluids cooled and crystallized. Amethyst geodes often form within basalt flows. Gas bubbles trapped in the lava created hollow cavities. Later, mineral-rich groundwater seeped into these spaces, depositing layers of quartz crystals. Trace amounts of iron within the quartz lattice produced the soft purple color associated with amethyst. In Uruguay, near the city of Artigas, large amethyst geodes have also formed. Some are large enough for a person to stand inside. Their interiors sparkle with countless crystal points, each reflecting light in gentle hues of violet. These geodes form through processes similar to those in Brazil, demonstrating how consistent conditions can produce similar crystal formations across continents. Moving to the island of Madagascar, you may envision pegmatite deposits containing enormous crystals of beryl, tourmaline, and feldspar. Pegmatites are known for their unusually large crystals, which grow from water-rich magma during the final stages of cooling. In Madagascar, some beryl crystals have reached lengths of several meters. Tourmaline crystals from Madagascar display a wide range of colors, often within a single crystal. These color variations result from changes in trace elements during growth. Layers of pink, green, and blue may appear in bands, recording subtle shifts in the chemical environment. In the Ural Mountains of Russia, emerald crystals have formed within metamorphic rocks. These green varieties of beryl owe their color to trace amounts of chromium and vanadium. The emerald deposits formed when hydrothermal fluids rich in beryllium interacted with chromium-bearing rocks under heat and pressure. Colombia is also famous for emeralds, particularly from the Muzo and Chivor regions. These emeralds formed in sedimentary rock rather than igneous or metamorphic environments. Mineral-rich fluids move through limestone and shale, depositing emerald crystals in veins and pockets. The clarity and deep green color of Colombian emeralds make them highly valued. In the Swiss Alps, clear quartz crystals known as rock crystal have been found in alpine fissures. These fissures formed as mountain-building forces fractured the rock. Over time, mineral-rich fluids entered the cracks and slowly deposited quartz crystals. The stable conditions within the fissures allowed crystals to grow with exceptional clarity. Japan is home to twin quartz crystals known as Japan law twins. These twins form when two quartz crystals grow together at a specific angle, creating a symmetrical V-shaped structure. The formation of these twins reflects precise conditions during crystal growth, including temperature and solution chemistry. In the United States, the state of Arkansas is known for its quartz crystal deposits. Quartz crystals from this region formed in hydrothermal veins within sandstone and shale. The crystals are often clear and well formed, reflecting slow growth in stable conditions. Another remarkable site is the Pulpi Geode in Spain, which contains large selenite crystals, a transparent variety of gypsum. These crystals formed in a cavity within dolomite rock, where mineral-rich water evaporated slowly, allowing large crystals to develop. In Namibia, the Brandberg mountain region is known for amethyst crystals of deep purple color. These crystals formed in volcanic rock cavities, where silica-rich fluids deposited quartz over long periods. Variations in iron content and natural radiation contributed to the intensity of the color. Australia also hosts notable crystal formations. In Western Australia, cricoid crystals form striking red prisms. These crystals developed in oxidized zones of lead ore deposits, where chemical reactions produced vivid coloration. In Queensland, smoky quartz crystals have been found in granitic regions. Their brown to grey coloration results from natural radiation altering the crystal lattice. These crystals formed slowly within granite, where silica-rich fluids allowed quartz to crystallize in open spaces. Iceland's volcanic landscapes contain deposits of calcite known as Iceland spar. This clear calcite exhibits strong double refraction, splitting light into two images. The crystals formed in basalt cavities, where mineral-rich fluids deposited calcite over time. Mexico's Chihuahua region is known for fluorite crystals that form in hydrothermal veins. Fluorite can display a range of colors, including green, purple, and blue, depending on trace elements and lattice defects. The cubic symmetry of fluorite produces distinctive geometric forms. China's Hunan province has yielded large stibnite crystals composed of antimony sulfide. These metallic crystals form long, slender blades with reflective surfaces. They developed in hydrothermal veins, where mineral-rich fluids cooled and precipitated stibnite. Each of these locations shares a common theme: stable conditions over long periods. Whether deep underground within volcanic rock or in evaporating cavities, crystals require patience to grow. Their size and clarity reflect the calm persistence of natural processes. Imagine drifting from one crystal site to another, each environment quiet and undisturbed. Beneath deserts, within mountains, inside caves and along coastlines, crystals form slowly, guided by temperature, pressure, and chemistry. As you picture these places, allow your thoughts to move gently, like a slow journey across the earth. There is no urgency in this travel, only a quiet appreciation for the steady processes shaping each crystal. Let your breathing match this calm exploration. Inhale as you arrive at a new landscape. Exhale as you observe crystals forming silently within it. With each breath, the journey continues, peaceful and unhurried. These famous crystal locations remind us that remarkable structures can form in stillness. Over immense spans of time, atoms arrange themselves into order, producing clarity, symmetry, and quiet beauty beneath the surface of the world. Rest with this thought, and imagine the earth itself breathing slowly, nurturing crystals in its depths, allowing them to grow in silence and balance. Take a slow, gentle breath in and imagine a clear crystal resting in your palm, cool and smooth, its surfaces reflecting soft light. This crystal is quartz, one of the most abundant minerals in the Earth's crust. Though often overlooked because of its familiarity, quartz is a remarkable example of stability, symmetry, and persistence in nature. Quartz is composed of silicon and oxygen, forming silicon dioxide with the chemical formula SiO2. Silicon and oxygen are two of the most common elements in Earth's crust, which explains the widespread presence of quartz. These atoms bond in a repeating tetrahedral structure, where each silicon atom is surrounded by 4 oxygen atoms. The tetrahedral units link together in a continuous 3-dimensional framework. Each oxygen atom is shared between 2 silicon atoms, creating a strong and stable lattice. This arrangement gives quartz its hardness, durability, and resistance to weathering. Quartz crystallizes in the hexagonal crystal system, often forming 6-sided prisms with pointed terminations. The external shape reflects the internal symmetry of its atomic structure. Even when quartz forms without visible crystal faces, its internal order remains consistent. One of the defining properties of quartz is its hardness. It ranks 7 on the Mohs scale, meaning it can scratch glass and resist abrasion. This hardness arises from the strong covalent bonds between silicon and oxygen atoms within the lattice. Quartz is highly resistant to chemical weathering. While many minerals break down over time, quartz remains stable under a wide range of conditions. This durability allows quartz grains to persist in sediments long after other minerals have dissolved or altered. Quartz forms in many geological environments. It crystallizes from magma in igneous rocks such as granite. It precipitates from hydrothermal fluids in veins and cavities. It recrystallizes during metamorphism, forming quartzite. It also appears as sand grains in sedimentary rocks. In igneous rocks, quartz typically forms during the later stages of cooling, when silica-rich melt solidifies. Because it crystallizes at relatively low temperatures compared to other minerals, quartz often fills spaces between earlier formed crystals. Hydrothermal quartz forms when silica-rich fluids move through cracks in rock and deposit crystals as temperature and pressure change. These veins may contain clear, well-formed crystals, sometimes called rock crystal. Such crystals can grow slowly in open spaces, producing smooth faces and sharp edges. Amethyst is a purple variety of quartz, colored by trace amounts of iron and natural radiation. Citrine, a yellow variety, forms when iron impurities and heat alter the crystal structure. Smoky quartz develops its gray to brown color through exposure to natural radiation that affects the lattice. Rose quartz, with its soft pink hue, owes its color to trace amounts of titanium, iron, or manganese. Unlike clear quartz crystals, rose quartz often forms in massive aggregates rather than distinct crystals. Its gentle color reflects subtle variations within the crystal lattice. Quartz can also form microscopic crystals known as microcrystalline quartz. Varieties such as chalcedony, agate, and jasper consist of intergrown quartz crystals too small to see individually. These forms often display banded patterns resulting from rhythmic deposition of silica. agates form when silica-rich fluids deposit layers within cavities, producing concentric bands. Each band represents a stage of crystal growth influenced by changing conditions. The resulting patterns reflect the steady, layered formation of microcrystalline quartz. Quartz plays a significant role in the formation of sand. As rocks weather, quartz grains remain intact due to their hardness and resistance to chemical breakdown. Over time, these grains accumulate to form beaches, dunes, and sandstone. In deserts, wind transports quartz sand across vast distances, shaping dunes that shift slowly over time. Each grain of sand is a tiny crystal fragment, worn smooth by transport, but still retaining its internal lattice structure. Quartz also exhibits piezoelectric properties. When mechanical pressure is applied, quartz generates an electrical charge. Conversely, when an electrical current passes through quartz, it vibrates at a precise frequency. This property makes quartz essential in watches, clocks, and electronic devices for accurate timekeeping. Quartz crystals vibrate at stable frequencies due to their uniform lattice structure. These vibrations regulate time in quartz watches, ensuring consistent measurement. The same principle is used in radio transmitters and other electronic systems requiring stable oscillations. Another optical property of quartz is its ability to rotate polarized light. This phenomenon, known as optical activity, occurs because of the asymmetrical arrangement of atoms within the crystal. Some quartz crystals rotate light clockwise, while others rotate it counterclockwise. Quartz often contains inclusions, such as tiny fluid bubbles, mineral fragments, or gas pockets trapped during growth. These inclusions provide a record of the environment in which the crystal formed. By studying them, scientists can estimate temperature and pressure conditions at the time of formation. Large quartz crystals can grow in pegmatites, where water-rich magma allows slow, uninterrupted growth. Some quartz crystals from pegmatites reach impressive sizes, reflecting stable conditions over long periods. In metamorphic environments, quartz recrystallizes to form quartzite. During this process, quartz grains fuse together, creating a dense, durable rock. Quartzite's resistance to weathering makes it a prominent feature in many mountain ranges. Quartz is also found in geodes, hollow rock cavities lined with crystals. These cavities form when gas bubbles in volcanic rock later fill with silica-rich fluids. Over time, quartz crystals grow inward from the cavity walls, creating sparkling interiors. Despite its abundance, quartz remains a symbol of clarity and balance. Its transparent varieties transmit light with minimal distortion, reflecting the uniformity of its internal structure. This clarity has made quartz useful in lenses, prisms, and optical instruments. Imagine quartz forming slowly within a quiet rock cavity, each atom settling into place, each bond strengthening the lattice. The crystal grows without haste, its structure guided by the steady availability of silica and stable conditions. As you picture this process, allow your thoughts to become clear and settled, like the crystal itself. The steady arrangement of atoms mirrors a calm mind, orderly and balanced. Let your breathing follow this gentle rhythm. Inhale and imagine the crystal growing. Exhale and feel the structure becoming more complete. With each breath, clarity deepens and stillness expands. Quartz reminds us that strength and stability can arise from simple, repeated patterns. Its presence in mountains, sand, and even timekeeping devices reflects its quiet importance in the natural world. Rest with this image of clarity and calm, and allow the steady structure of quartz to guide you toward peaceful stillness. Take a slow, calm breath in, and imagine discovering a crystal unlike any you have seen before. A form shaped by uncommon conditions, rare elements, or delicate balances within the earth. While many crystals follow familiar patterns, some form in extraordinary ways, revealing the wide range of environments in which order can emerge. Rare crystal formations often develop where chemical conditions differ from the norm. Unusual combinations of elements, temperature ranges, or pressure levels can produce minerals that are seldom found. These crystals may be small, fragile, or hidden deep within rock, waiting patiently for discovery. One example is bismuth crystals, which can form stepped, geometric patterns. Although natural bismuth crystals are rare, they sometimes develop in hydrothermal veins. Their distinctive hopper shapes arise when crystal edges grow faster than their centers, producing stair-step patterns that reflect the internal lattice. Hopper crystals form when growth occurs rapidly along edges while the center lags behind. This pattern can appear in minerals such as halite and galena under certain conditions. The resulting skeletal shapes provide a glimpse into the dynamics of crystal growth. Another unusual formation is the desert rose, a rosette-shaped cluster of gypsum or barite crystals. These formations occur in arid regions where mineral-rich groundwater evaporates. Sand grains become trapped within the growing crystals, producing petal-like structures that resemble blooming flowers. Desert roses form through repeated cycles of moisture and evaporation. As groundwater rises and evaporates, gypsum crystallizes around sand grains. Over time, layered crystal growth produces the rosette form, each petal reflecting the alignment of tabular crystals. Selenite crystals, a transparent variety of gypsum, can form delicate blades that intersect in intricate patterns. In some caves, selenite forms clusters resembling frozen waterfalls, where countless crystals grow side by side in quiet symmetry. Another rare crystal is croquat, a vivid red mineral composed of lead chromate. Croquite crystals form elongated prisms with bright coloration due to chromium. They develop in oxidized zones of lead ore deposits, where chemical reactions create conditions suitable for their growth. Azurite and malachite provide examples of copper minerals that form striking blue and green crystals. These minerals develop in the oxidation zones of copper deposits, where groundwater interacts with copper-bearing rocks. Azurite often forms deep blue crystals, while malachite forms banded green masses or fibrous crystals. Opal is a unique mineral that differs from typical crystals because it lacks a regular lattice structure. Instead, opal consists of tiny silica spheres arranged in a repeating pattern. This structure diffracts light, producing shifting colors, known as play of color. Precious opal forms under specific conditions, where silica-rich water deposits layers of microscopic spheres. Fire opal, found in volcanic regions, displays warm hues of orange and red due to trace elements. Unlike precious opal, It may lack play of color, yet its translucent glow reflects the gentle deposition of silica in cavities. Fluorite can form crystals that fluoresce under ultraviolet light. Trace elements within the lattice absorb ultraviolet radiation and emit visible light, producing glowing colors. This property, known as fluorescence, highlights the interaction between crystal structure and light. Another unusual formation is the fulgurite, created when lightning strikes sandy soil. The intense heat melts the sand, fusing it into glassy tubes that follow the path of the electrical discharge. Although not true crystals, fulgurites demonstrate how sudden energy can transform materials into structured forms. Native sulfur crystals form near volcanic vents, where sulfur gases condense and crystallize. These bright yellow crystals often grow in delicate clusters, reflecting the cooling of sulfur vapor in a calm environment following volcanic activity. Halite crystals can form delicate hopper shapes in evaporating salt pans. When evaporation occurs rapidly, crystal edges grow faster than their centers, producing hollow, stepped forms. These structures reveal how growth rates influence crystal morphology. Some rare crystals form only under very specific pressure conditions. Coesite, a high-pressure form of silica, develops during meteorite impacts or deep within the Earth's mantle. Its formation requires pressures far greater than those at the surface, making it a rare indicator of extreme conditions. Another high-pressure mineral, stishovite, also composed of silica, forms under intense pressure conditions. Its dense structure reflects the rearrangement of atoms into a more compact lattice. These minerals provide evidence of powerful natural events, such as meteorite impacts. In caves, aragonite crystals can form delicate needle-like clusters known as cave frost. These crystals develop when mineral-rich water evaporates quickly, causing rapid precipitation. Their fragile, branching forms highlight the sensitivity of crystal growth to environmental changes. Some crystals form inclusions that create unusual visual effects. Rutile needles within quartz produce a golden, hair-like appearance known as rutilated quartz. These inclusions formed when rutile crystals grew first and were later enclosed by quartz. Phantom crystals display faint outlines of earlier growth stages within a single crystal. These patterns form when growth pauses and resumes under different conditions, leaving visible layers that mark the crystal's history. Geodes with rare mineral linings offer another example of unusual formations. While many geodes contain quartz, some are lined with celestite, calcite, or barite crystals. These minerals crystallize from fluids entering the cavity long after the host rock formed. Even ice can form unusual crystalline structures. In extremely cold conditions, hoarfrost creates delicate, feathery ice crystals on surfaces. These crystals grow from water vapor, forming intricate patterns that reflect the hexagonal symmetry of ice. Uncommon crystal formations remind us that nature's processes are both consistent and diverse. Small variations in chemistry, temperature, or pressure can produce entirely different structures, each reflecting the conditions of its formation. Imagine discovering one of these rare crystals in a quiet place, its form shaped by unique circumstances, its structure a record of subtle environmental changes. There is a sense of calm in knowing that even the rarest formations arise from the same steady principles of atomic order. As you rest, picture these unusual crystals forming slowly, guided by conditions that shift gently over time. Each breath mirrors the quiet patience required for their growth. Inhale, and imagine atoms arranging themselves into rare patterns. Exhale, and see the crystals form, becoming more defined. With each breath, the process continues, calm and unhurried. Rare crystals remind us that even in uncommon condition order emerges. Their forms, though unusual, reflect the same quiet balance found in more familiar crystals. In their stillness, there is a sense of wonder that invites peaceful reflection. Let your thoughts settle like crystals in a calm solution, forming patterns unique to the moment, yet guided by steady principles. In this quiet formation, rest comes naturally. Take a slow, steady breath in and imagine a crystal forming in a calm, hidden space. Though the crystal grows according to its internal structure, the environment around it plays a profound role in shaping its size, clarity, and form. Temperature, pressure, chemistry, time, and available space all influence how crystals develop in nature. Temperature is one of the most significant environmental factors affecting crystal growth. In warmer conditions, atoms and ions move more rapidly, making it harder for them to settle into stable positions. As temperatures decrease, atomic motion slows, allowing bonds to form and lattices to develop. This gradual calming of motion supports the growth of well-ordered crystals. Slow cooling often produces large crystals. When magma cools deep underground, atoms have time to migrate and attach to growing crystal surfaces. This extended growth period results in coarse-grained rocks with visible crystals. In contrast, rapid cooling at the surface produces fine-grained textures or glass, where atoms lack time to arrange into lattices. Pressure also shapes crystal growth. Deep within the Earth, immense pressure compresses atoms into denser arrangements. Certain minerals only form under high-pressure conditions, where atoms are forced into compact structures. At lower pressures, different minerals may form from the same chemical components. Directional pressure can influence crystal orientation. In metamorphic environments, elongated minerals align perpendicular to the direction of greatest force. This alignment produces foliation, creating layered textures in rocks such as schist and slate. The orientation of crystals reflects the pressure environment during formation. Chemical composition of the surrounding environment determines which crystals can form. Mineral-rich fluids carry dissolved ions that crystallize when conditions change. If silica is abundant, quartz may form. If calcium and carbonate are present, calcite may precipitate. The availability of elements guides the crystal growth process. Impurities in the environment can alter crystal appearance. Trace elements incorporated into the lattice may change color, transparency, or growth patterns. Iron can produce reds and yellows. Chromium can create greens, and manganese can contribute pink hues. These subtle inclusions reflect the chemical diversity of the environment. Water plays a vital role in many crystal-forming environments. It dissolves minerals, transports ions, and facilitates chemical reactions. In hydrothermal systems, hot water carries dissolved silica and metals through rock fractures. As temperature and pressure change, minerals crystallize, forming veins rich in quartz and other minerals. Evaporation influences crystal growth in arid environments. As water evaporates, dissolved minerals become concentrated, leading to supersaturation. Crystals begin to form and grow as ions bond into stable structures. Salt flats, gypsum deposits, and evaporate layers all reflect this environmental process. Available space affects crystal shape. In open cavities, crystals grow freely, developing well-formed faces that reflect their internal symmetry. In crowded environments, crystals compete for space, producing irregular or interlocking shapes. The resulting texture records the spatial constraints during growth. Time is essential for crystal development. Slow, uninterrupted growth allows atoms to align properly, producing clarity and symmetry. Rapid changes in conditions may interrupt growth, resulting in smaller crystals or zoning patterns. The duration of stable conditions directly influences crystal size. Fluctuating environments can produce layered crystals. Changes in temperature, pressure, or chemical composition during growth may create bands or zones within a crystal. These layers record environmental variations, preserving a timeline of changing conditions. Radiation in the environment can alter crystal color. Natural radiation can displace atoms within a crystal lattice, creating color centers that absorb specific wavelengths of light. Smoky quartz, for example, owes its color to radiation affecting aluminum impurities within the lattice. The acidity or alkalinity of water also influences crystal formation. Acidic conditions may dissolve certain minerals, while alkaline conditions promote precipitation. Calcite, for instance, precipitates when carbon dioxide levels decrease, allowing calcium carbonate to crystallize. Biological activity can indirectly influence crystal growth. Organisms may alter chemical conditions in soil or water, affecting mineral precipitation. Shells and coral structures composed of calcium carbonate demonstrate how living systems can create environments conducive to crystal formation. Seasonal cycles can drive repeated crystallization. In regions with alternating wet and dry periods, minerals dissolve during wet seasons and crystallize during dry seasons. Over time, this cycle builds layered deposits that reflect environmental rhythms. Wind and air movement influence evaporation rates, affecting crystal size and shape. Rapid evaporation may produce smaller crystals, while slower evaporation supports larger, well-defined forms. Airflow can also deposit fine particles that become inclusions within growing crystals. Gravity affects crystal growth in fluid environments. Denser ions may settle, influencing concentration gradients. In magma chambers, dense crystals sink, while lighter ones remain suspended. This separation alters the composition of the remaining melt, shaping subsequent crystal formation. The presence of surfaces or nucleation sites influences where crystals begin to grow. Rough surfaces, fractures, or existing mineral grains provide locations where atoms can attach and form stable nuclei. Without nucleation sites, crystallization may be delayed even in supersaturated solutions. Environmental stability is key to producing large, clear crystals. In caves, underground chambers, and deep rock fractures, conditions often remain stable for long periods. These calm environments allow uninterrupted growth, producing crystals of remarkable size and clarity. Conversely, dynamic environments produce irregular or fragmented crystals. Rapid temperature changes, mechanical disturbance, or chemical fluctuations interrupt growth, resulting in smaller or deformed crystals. These variations reflect the history of environmental change. Imagine a crystal forming in a quiet cavern, untouched by sudden change. The air is still, the temperature steady, and mineral-rich water drips slowly from above. Each drop deposits ions that settle into the growing lattice. Over centuries, the crystal becomes larger, clearer, and more complete. As you picture this environment, allow your thoughts to become equally steady. The calm surroundings support gentle growth, free from disturbance. Each breath mirrors the stable conditions that nurture crystal formation. Inhale and imagine the environment cooling slightly, encouraging atoms to settle. Exhale and picture the crystal expanding, its structure becoming more refined. With each breath, growth continues, quiet and balanced. The environment shapes crystals, just as surroundings influence our own sense of calm. Stable conditions support clarity and order, while gentle changes create subtle variations. In this balance between constancy and change, crystals form with quiet resilience. Let your breathing slow further, matching the steady pace of environmental rhythms. In this calm stillness, crystal growth continues, guided by the surrounding world and the passage of time. Take a slow, calm breath in and imagine a crystal resting in soft light. At first, it appears clear, but as the light shifts, delicate colors emerge: violet, gold, green, or soft pink. These colors are not random. They arise from subtle changes within the crystal, often caused by tiny amounts of other elements, known as trace elements. Pure crystals are often colorless because they transmit light without absorbing specific wavelengths. Quartz, for example, is naturally clear when composed only of silicon and oxygen. However, when small amounts of other elements enter the crystal lattice, they alter how light is absorbed and reflected, producing color. Trace elements are atoms that substitute for the primary atoms in a crystal structure. Because these elements have slightly different sizes or electrical properties, they change how the crystal interacts with light. Even a tiny concentration can create noticeable color. Iron is one of the most common trace elements responsible for crystal color. In quartz, iron can produce the purple color of amethyst. Natural radiation alters the iron within the lattice, creating color centers that absorb specific wavelengths of light. When heated, amethyst may turn yellow, forming citrine as the iron changes its state. Chromium is another powerful coloring agent. In the mineral corundum, chromium produces the deep red of ruby. Without chromium, corundum is colorless. With small amounts of iron and titanium instead, corundum becomes sapphire, displaying shades of blue. Manganese can create pink hues in minerals, such as rhodochrosite and rose quartz. In rose quartz, the color is soft and milky, often caused by microscopic inclusions or trace elements within the structure. The gentle pink tone reflects subtle variations in composition. Copper produces striking blue and green colors in minerals such as azurite and malachite. These minerals form in the oxidation zones of copper deposits, where chemical reactions introduce copper ions into the crystal structure. The resulting colors reflect the way copper absorbs and reflects light. Nickel can produce green coloration in certain minerals, while cobalt can create vivid blue hues. These elements substitute for other atoms in the lattice, altering the energy levels of electrons and changing how light is absorbed. Some crystal colors result from structural defects rather than trace elements. In smoky quartz, natural radiation displaces atoms within the lattice, creating color centers that darken the crystal. The gray to brown coloration reflects changes in electron behavior caused by these defects. Fluorite displays a wide range of colors, including purple, green, blue, and yellow. These variations result from trace elements, lattice defects, and exposure to radiation. Fluorite can also fluoresce under ultraviolet light, emitting visible colors as electrons return to lower energy states. Color zoning can occur when trace element concentrations change during crystal growth. A crystal may display bands of different colors, each representing a stage in its formation. These zones record shifts in environmental conditions such as temperature, pressure, or chemical composition. Tourmaline often exhibits dramatic color zoning. A single crystal may display pink, green, and blue bands along its length. These variations occur as trace elements in the surrounding fluid change during growth. Each band reflects a moment in the crystal's history. Inclusions can also influence crystal color. Tiny mineral fragments, gas bubbles, or fluid pockets trapped during growth may scatter light, creating cloudy or shimmering effects. Some inclusions produce special optical phenomena, such as the star-like patterns seen in star sapphires. Opal displays shifting colors through a different mechanism. Instead of trace elements, opal's play of color results from the diffraction of light by microscopic silica spheres arranged in a regular pattern. The spacing between these spheres determines which wavelengths of light are reflected. Temperature can influence color formation. Heating can alter the state of trace elements, changing how they interact with light. For example, heating amethyst may transform it into citrine by altering the oxidation state of iron. Radiation in the environment can create or intensify crystal color. Natural radiation from surrounding a sukur can displace atoms, forming color centers. This process contributes to the colors of smoky quartz and certain varieties of fluorite. The thickness of a crystal can affect perceived color. Thicker sections absorb more light, appearing darker, while thinner areas appear lighter. This effect can create gradients within a single crystal. Some crystals change color under different lighting conditions, a phenomenon known as pleochroism. In pleochroic minerals, light is absorbed differently along different crystallographic directions. This property causes the crystal to display different colors when viewed from different angles. Tanzanite is a well-known pleochroic mineral, showing blue, violet, and burgundy tones depending on viewing direction. This effect arises from the anisotropic structure of the crystal, which interacts with light differently along different axes. color in crystals can fade over time if exposed to prolonged sunlight or heat. Ultraviolet radiation may alter color centers, reducing intensity. This sensitivity reflects the delicate balance of atomic arrangements that produce color. Some crystals are artificially treated to enhance color. Heat treatment, irradiation, and dyeing can alter or intensify hues. However, natural coloration remains a record of the crystal's formation environment and chemical history. Imagine a crystal growing slowly in mineral-rich fluid, tiny amounts of trace elements entering its lattice. Each addition alters the way light moves through the structure, creating gentle hues that reflect the surrounding environment. As you picture this process, allow your thoughts to soften like the colors within the crystal. Subtle variations create beauty, just as small moments shape a calm state of mind. Let your breathing remain slow and steady. Inhale and imagine light entering the crystal. Exhale and see soft colors emerging, calm and balanced. With each breath, the crystal's hues deepen, reflecting quiet harmony. Crystal colors remind us that even the smallest changes can create remarkable variation. A few atoms, a slight shift in conditions, or a trace element can transform clarity into color. In this delicate balance, nature paints in quiet tones. Rest with this image of gentle color and calm light. Allow the soft hues of imagined crystals to guide you toward peaceful stillness, where subtle beauty unfolds without effort. Take a slow, steady breath in and imagine entering a quiet cavern deep beneath the earth. The air is still, the temperature steady, and the walls shimmer with countless crystal faces reflecting soft, diffused light. In places like this, crystals have grown slowly and undisturbed for thousands of years, forming structures of astonishing size and clarity. Crystal caves form when mineral-rich water fills underground cavities and remains stable for long periods. These cavities may originate as gas bubbles in volcanic rock, fractures created by tectonic forces, or spaces dissolved by groundwater in limestone. Once formed, they provide protected environments where crystals can grow without disturbance. One of the most remarkable examples of giant crystal growth is found in the Cave of the Crystals in Naca, Mexico. This chamber contains enormous gypsum crystals, some exceeding 10 meters in length. These crystals formed in warm, mineral-rich water that remained at a steady temperature for thousands of years. The Naca crystals grew under highly specific conditions. The cave was filled with water, saturated with calcium sulfate. At temperatures around 58 degrees Celsius, anhydrite, a related mineral, became unstable and dissolved. As the solution cooled slightly, gypsum crystallized, forming massive, transparent beams that continued to grow uninterrupted. The stability of temperature and chemical composition in the cave allowed crystals to grow slowly and uniformly. Even small fluctuations could have interrupted growth. Instead, the environment remained steady, allowing atoms to attach to crystal surfaces in a continuous process. Gypsum crystals in Naca are composed of calcium sulfate and water molecules arranged in a layered structure. This structure allows crystals to grow into elongated forms. The clarity of these crystals reflects the purity of the solution from which they formed. Another notable crystal cave is the Pulpi geode in Spain. This geode contains large selenite crystals, a transparent variety of gypsum. The crystals formed in a cavity within dolomite rock, where mineral-rich water evaporated slowly, allowing crystals to grow inward from the walls. Unlike the towering crystals of Neiwa, the Pulpi crystals form interlocking blades that fill the cavity. Their growth reflects the gradual evaporation of mineral-rich water, leaving behind layers of crystalline gypsum. In limestone regions, caves often contain calcite formations. While not always forming giant single crystals, calcite can accumulate in thick layers, producing stalactites, stalagmites, and flowstone. These structures consist of countless microscopic crystals deposited over long periods. Calcite crystal caves can display sparkling surfaces known as druses, where small crystals cover rock walls. Each tiny crystal reflects light, creating a gentle shimmer that fills the cavern with soft radiance. Quartz crystal caves are less common, but can form in hydrothermal environments. Silica-rich fluids entering rock cavities may deposit quartz crystals that grow inward over time. In stable conditions, these crystals can reach impressive sizes, forming clusters of clear or smoky quartz. Temperature stability is essential for the growth of giant crystals. Fluctuations can cause dissolution or irregular growth. In deep caves, the surrounding rock acts as insulation, maintaining steady conditions that support slow, uninterrupted crystallization. Water chemistry also plays a crucial role. The concentration of dissolved minerals must remain within a narrow range to allow growth without rapid precipitation. If the solution becomes too saturated, crystals may form quickly but remain small. If it is undersaturated, existing crystals may dissolve. Time is perhaps the most important factor in giant crystal formation. Growth rates are often extremely slow, sometimes only fractions of a millimeter per year. Over thousands of years, this gradual accumulation produces crystals of extraordinary size. Crystal caves provide natural laboratories for studying mineral growth. Scientists examine fluid inclusions, crystal structure, and chemical composition to understand the conditions that allowed such growth. These studies reveal the delicate balance required for large crystal formation. Humidity within caves influences crystal stability. High humidity prevents dehydration of minerals like gypsum, preserving their structure. If humidity drops, gypsum can lose water and transform into other minerals, altering the crystal form. Airflow within caves can affect evaporation rates. Gentle airflow may promote slow evaporation, supporting crystal growth. Strong airflow, however, can cause rapid drying, leading to smaller or damaged crystals. Light rarely reaches deep crystal caves, preserving delicate formations. Without exposure to sunlight, crystals remain protected from temperature fluctuations and radiation that might alter their color or structure. Some caves contain aragonite crystals, forming delicate needle-like clusters. These formations develop when mineral-rich water evaporates quickly, causing rapid precipitation. Though fragile, they demonstrate how variations in conditions produce different crystal forms. In volcanic regions, lava tubes may contain mineral deposits where groundwater interacts with cooling rock. Over time, Crystals form along the walls of these tubes, creating sparkling interiors that reflect the slow movement of mineral-rich fluids. Ice caves provide another example of crystal growth. In cold environments, water vapor can freeze into ice crystals on cave walls, forming delicate structures. These crystals grow from vapor deposition, reflecting the hexagonal symmetry of ice. Imagine standing quietly within a crystal cave, surrounded by formations that took thousands of years to develop. Each crystal reflects a history of steady conditions, mineral-rich water, and the passage of time. As you picture this calm environment, allow your thoughts to slow. The still air, the steady temperature, and the gentle shimmer of crystals create a sense of deep quiet. Let your breathing match the slow growth of these formations. Inhale and imagine mineral-rich water touching a crystal surface. Exhale and see a new layer forming, smooth and clear. With each breath, the crystal grows, unhurried and complete. Giant crystals remind us that remarkable structures arise from patience and stability. In protected spaces, free from sudden change, atoms assemble into forms of clarity and strength. Rest with this image of a quiet cavern filled with gentle light and towering crystals. In the calm of this imagined space, allow yourself to drift toward peaceful stillness, guided by the steady rhythm of crystal growth.